next week on Thursday. Maybe I will finish all the results from this class. Okay, so yeah, but I think I will announce before Thursday, like if I can finish on time. Okay, if not, then maybe uh, next 2 weeks. Next 2 weeks on Tuesday, maybe. Okay, if not next week, Thursday. Okay. Yeah. How are you feeling about the midterm? Is it uh, difficult? Okay. Yeah. That's true. That's true. The midterm should be difficult because I want to appreciate the students. But actually, in my opinion, how I grade the score or how the results will be, um, it's not always depends on the uh, the standards from the university. For example, if the standards say that I forgot the standard, if you have the minimum passing score is around 60 something, okay, yeah, around 60, yeah, 60. Maybe for my class, because I usually calculate based on statistics. So I will try to get some input and try to make some normal distributions. And from that statistics, I will get some uh, average score and at least the minimum passing score. And usually in my class, it will be lower than 60 to get passing. Okay. So for example, if you get if my passing is if my passing score is around 53 or 54, it can be it can be, and it's dependent on the statistic on this class. Okay. And of course, the statistics on this class will be different from the other class as well. Okay, so it really depends on how you absorb the study, the learning, okay, and also on your results. Okay, so your score, for example, if there are a lot of maybe who got really high, then I need to also take sometimes to take the results into some statistic, okay, approach, and from the statistics I can give you the score. Okay, and it doesn't mean that if you get really low, it doesn't mean that you will be maybe fail for the midterm. No, uh, because we have some other percentage, right, from the quiz, from the final. Okay, and yeah, I think we can wait uh, for your results first, and you can at least calculate based on the quiz that you already have, and also with your expected results on your midterm. Okay. Okay, how about the time for the midterm? Is it sufficient or not really? What do you think? Do you think the time should be longer? Should be longer? Okay, if the time is longer, then okay, I can do it more. Or because sometimes, even though the time is longer, you cannot think anything else in your mind. So you start. Yeah, sometimes. Like for example, the questions that is maybe you need to write a lot of things, then maybe you need longer time. Okay. Yeah, yeah. That's why before writing, maybe think something first. Maybe you need to have some simplification of some sort. Yeah, but that is the point. Yeah. And I think if you check the question, I put the points, right? Like 6 point, 5 point. That is to suggest that in exam, aside from working on the questions, you need to also take some priority. Which question you need to work first? You see the point, and when you think that I need more time for this question, but the point is too low, maybe you need to look for other question first. That is maybe higher point, but oh, I think I can do it. You can do that first. So if you skip like a few questions that is not really that much, that's still okay, right? If you can get higher from other questions. And then maybe at the last 20 minutes or 30 minutes, you can tackle the smaller problems that you can do. Okay. So you start with like you start with working with something that is uh, maybe the point is not that highest, but maybe it's okay, and you think you can do it, because sometimes I give you like the more points it had, it should be the difficulty should be higher. Should yeah yes yes yes. But I think the middle one, I think that one is okay to be tackled first. Yeah. Okay. So yeah, based on the previous year, also the last 2 years, also uh, some students, even when they are already know how the question will be, they already think like, okay, skip several questions and then focus on another part. Okay? Because when the time is running out, uh, you can at least predict your own score, and that is usually a strategy. If you if you I'm not sure, some tests like in a if you want to get some certificate work or anything else that is similar to what I've been given, that is usually the way you need to work on. Okay, okay. I think yeah, I might need some feedback from you for our midterm, but I think I will just ask that one next week. For today, we can start a new chapter in calculus, a new perspective. Okay, so on chapter 1, chapter 4, until chapter 4, mostly that is we talk about derivative, right? First derivative, second derivative, applications, right, and other stuff. The second part of our calculus in the semester is about integration. Okay, okay. Let me go to. Okay, before I forgot. Okay, I want to know who this student. I forgot to take notes. The student ID. This is before the midterm. Anyone know who is the never gonna say goodbye? Maybe from online students. Anyone know who these students? If he's not showing up, maybe I will just ask in the Moodle later. Okay. Okay, funny. Okay, we can start the course for a while. Let me go through. Okay. So hopefully I can give you for today a brief intro and a little bit um, what will we what will we do in the rest of the semester. And because uh, our midterm is on late November, okay, uh, then because I think one student asked me when is the final exam, right? And based on what we will do, uh, I think we will have, if you check the schedule, okay, the final exam is the ending on, I think, 10 January, I think. If I can schedule exam for this class before 10, then I think it's good. We can be actually running, okay, for the rest of the semester. But if not, maybe the final exam will be around this this dates, okay? Maybe, okay, a little bit delay. So I will have a 1 week additional time. But if not, then we can have maybe around this, maybe between 8 to 10, maybe 8 to 10 between that schedule. And the rest of the lecture, if I cannot provide in class, I will provide in a short video, maybe 15 minutes video for you, okay, for some parts, okay, that is uh, important. Okay. Okay. Okay, I think we can start. So first, we start with the area. Okay. So if we look at this, the just a random function f, okay, so y equal f of x, okay, and you're looking at from x equal a, okay, and x equal b, and if you just look at this interval and look at this function here, and the integration or the integrals is actually talking about what the area under the curve, right? Okay, and then I think some of your, most of you already know that. So that will be our problem in these chapters. Okay. So we attempt to finding area of region S that lies under y equal f of x from A to B. Okay. Okay. Now, to find this area, of course, we need to approach with some geometric, okay, and because it has some curve, it's, I think it's a little bit difficult to get what object or what geometry that we can approach. For example, we can think maybe this triangle, rectangle, triangle, or any polygons that we can think of, okay, that is fit with our curve, okay. And of course, if we are going to slice, okay, let's say we slice this. This slice become something really small, and if we look at, if we take, maybe we imagine there is a rectangle below here. Okay. Maybe we can take some approach for this curve using this rectangle. At least the rectangle here, there's a lot of rectangle. The trans is going to fit within the curve with some exceptions, that is we have a gap here, right? So if we looking here, let me take this here. So if we take some, I think this is x squared. Yeah, x squared. This x squared here. We take into four area, and we approach each area becomes our rectangle here. Okay. Of course, we are having some over area, right? Something that is not similar with our goal. Okay, we need to find this area. Okay, and also uh, imagine that we are having more rectangles, and if you look here, we can take the rectangle below the curve. Okay, so below the curve, this is using the left endpoint, which means the left endpoint is perfectly up below this curve, and then we have this rectangle. Or using the right endpoints. So how to use that? If you see here, it starts from this left endpoint that is touching the curve. Okay? So the left endpoint here touching the curve. Okay. So if you have the rectangle, the left endpoint is this one. This is left. And if you have the right endpoint that is touching is right. Okay. So the left endpoint is touching this curve, and you see that the rectangle is under the curve. Okay, the rectangle is under the curve, and we will see the gap that is uh, between the curve and the rectangle, right? If we compare these two, and we look at the right endpoint, the right endpoint means that this right end from the rectangle is touching the curve. Okay. If we compare, the difference is this is less, right? Less than the actual area that we want to compare because it's lost this space, right? It has this space. This one, it has the overlay space here, that another additional area. Okay, additional area. Okay, we usually call this case it's overestimate. Okay? It's overestimate. And this part here is underestimate. Okay, and of course, based on the number that we have here from 1 over 8, and we know the curve is the x squared. So from x equal 1 over 8, we know the functions, the results for y, and we can take some multiplications, right? And we can multiply this, the base and the height, and plus them, plus, and we have some number, okay? If I am going to, so if we are going to, let's say, the area for the left endpoint, let's say the x, and then multiply with f of x. I think I can write, let me put into a little bit higher so that I can write below here. Okay, wait. I think let me estimate this first, okay, because it's easier number than the below one. Okay. So the L4, that is the rectangle, 4 rectangle. So 1 over 4. This is, wait, this is the right endpoint. Oh, wait, okay, I think this one. This is the right endpoint. So 1 over 4, 1 over 4 squared plus 1 over 4. Let me move this a little bit left. Okay. And then plus 1 over 4. And then 3 over 4. And 1 over 4. And then 1 squared. Okay. This is based on this rectangle here. Oh, I didn't put the left one. Okay, but yeah, if you can imagine the left one. Forgot to put the left one. Later I will put for you. The left one should be from here, and then from there. Let me make. Okay, at least that yeah, not really proportional, but it's at the left end point. Okay, and the number will be similar, I think. 1 over 4, 1 half, 3 over 4, 1. Okay. If you look for the left end point here, let's write as L4. It starts from 1 over 4 and then from 0. Okay, we start from 0 point. And also 1 over 4 and 1 over 4 squared, and then 1 over 4 half squared, 1 over 4, 3 over 4 squared. Okay. If you look here, the R4 is equal 0.46875. The left one is 0.21875. Okay, you don't need to count. So you see that there is a gap between this number, and you'll see that if we look at how the graph is, our area is between this number, right? Okay. Now, of course, if you do the same thing with this one, if we divide with 1, 2, 3, 4, 5, 6, 7 rectangles. So we have 7 rectangles. 1, 2, 3, 4. This is 8 and 7 rectangles. Okay. So if we have this will be resulting. If you use the same way to calculate, the right end point will be around 0.3984. Okay, and the left, this is 8. This is around 0.273 something 4. Okay. Okay. Now look at the number. Okay. 2146. Okay. This is from the four rectangles. Okay, 4 rectangles. We take 4 rectangles. And if we take more, we cut more. It began to, the left one began to increase, the right one began to lower. And we want to make, or we want to approach this A, right? And if you think from here, from this 0.4 and 0.21, it should be around 0. Maybe 3 something, Okay. If you look here, the area that we want is between this number, right? Okay. And if you think logically, if you have more rectangles, we can have some numbers that is approaching this A, right? Okay. If we have a lot of rectangles. Okay, that's just a brief intro for on how we are looking this integrations problem. Okay. So integrations by definition in this case is not just an antiderivative, but it is actually our approach to calculate the area under the graph. Okay. Okay. Let me take some notes for you. Okay. Okay. Now, if we have this, look at here. This is 10 rectangle. Okay. The n is 10, and then we increase 30. We increase 50. Look at how the results. Okay. 0.385, and then you got 3502, and then we increase the n, and we have 3434. Okay, and if you see the visuals, okay, how the rectangle looks like, it's getting to be smaller, and it tends to be getting closer to the curve, right? Okay, this is just to give you a visuals idea. Okay? Because I believe using these visuals, this graph, is better way to imagine on how the things in integration will be. And more, I think more problems in the integrals is you need to, sometimes you need to visualize to understand. Okay. Either we need to find the area and maybe later the volume. It will be better if we have some visuals on our mind first. Okay. So this is the how it looks like here. Okay. Okay. And same thing if you check the left endpoint. This is right endpoint. Same thing if you check the left endpoint. And then the left endpoint is around this. If n is increasing to 30, the area will be approaching, should be approximate, should be around 3169, and n50 should be around that 3234. So I think our ideal area between this 3234 and 3434, that's around 33 maybe, 33 probably. Okay. Now, if we just using just random functions, okay, just go back to what we have from the beginning. That is, we have interval a to b. We have the y equal f of x, okay, and we define this. Take some, let's say s1. Okay, s1, s2, blah blah blah, and then until some sn. And this part here will be from between A, B, we have, let's say, x1, x2, x3 until sometime, let's say here is xn minus 1. Okay. Now the interval, the rectangle here, we can have a base, okay, that is our delta x. This is actually based on the interval AB and depends on how many rectangles we have. Okay, the n. So this will be the base or the width of the interval. So let's say the x0 is our first interval A, and our xn is our nth interval, our B. That is, we define that x1 is A plus delta x. Okay, and x2 means that we have delta x, right? 2 delta x, okay, and 3 delta x, 4 delta x, and so on. And we can define this into our x1, x2, 3 until n. Okay. And in general, we can have some xi for some n number. Okay? That is a plus I delta x. Okay. Now, if we take approach, okay, you can take it. You can choose between, because I already showing you the left hand method and right hand method. You can have at least now 2 ways to approach this rectangle. Okay, and let's say we are going to approach with the right endpoint. So I will have this. Okay. I will have this right endpoint. So our right endpoint, let's say I will write Rn for the area of the right end method. This will be, okay, okay. Simply, we are just taking the delta x, multiply with the height, the functions, right? And we plus all of this rectangle. Okay, it's still similar what I talked before. But then imagine when n, okay, imagine n is going to take approach into some infinity, okay? Which means that we take the n, like from the previous one. Imagine we take the n 4, and then 8, and then 10, and then 30, 50, and maybe 1,000, 10,000. And we are going to see that the rectangle we're going to be approaching the curve really smooth, right? Really smooth. So we need the concept of limit. Okay, we need the concept of limit to approach how large the uh, or how large the n is. Okay. Okay. Then the area of region S that lies under the graph of continuous function is the limit sum of the areas of approximating rectangles. That is a we take this first, okay, before we go into uh, the next definitions. Okay. And the same way, we can take the same approach for the left endpoint. Similar, similar structure. Okay. But okay, instead trying to look at right or left, instead of that, we can take uh, the curve into a sample point. Okay, a sample point. So we are not looking left or right, okay, but maybe where's my image here? Maybe we are taking on some sample points that is maybe from here, sample point, and we name it like x1 with asterisk. Maybe not really clear. Let me write below sample point 1, and maybe sample point 2 is maybe around here. So we can have more sample points, and we can write more general equations. Let me take this. Let me take it a little bit smaller. And we can take more general approach of our limit by using those sample points. So we don't really need to be uh, considered left or right anymore, because we just take some sample points in between left or right. Okay. Okay. Now let me write in the new page. Okay. Okay. Usually we write the sum using the notation of the sigma. I hope you still remember. So if I have sigma from I equal 1 until some n, which means this is actually f I dx is equal, this is x1 delta x plus f x2 delta x and plus until some n. Okay, that is the sigma notation. So sigma notation. Okay, so the expressions can be written as limit as n approaches infinity of sigma oh, we have a sample point. Okay, sorry, forget the asterisk. Okay, now the sigma notations, some notes before you. Let me write here. I think I have time. I will explain why it's happened. So if I have this is n, okay, and if I have the sigma I, okay, this will be n plus 1 over 2. Okay. This is actually from, if you remember the sequence and series, okay, so 1 plus 2 plus 3 plus 4 plus 5 plus until some n. And if you want to take the sum of this as n is equal precisely this, okay? Okay, but I think I will not explain that into more details there. And if I have I squared, this will be n plus 1, n plus 2n plus 1 divided by 6. And if I have I cube, this will be n plus 1 divided by 2 squared. Okay, this is actually, the sigma is actually how we are going to check the area under the curve. Okay, not using directly integral. Okay, so this is before we learn integral. Okay, and I just take some time for this notes. In the calculus part later, it's not really how to say that, applicable really well in some problems later. But actually, what you do when you have integration, they will take that number, the interval, and they put into here, and they will calculate for you. For example, if you write in your calculator, you want to take some integrals for some functions that maybe difficult functions that maybe it's also difficult if you integral using the antiderivative. Your calculation in your calculator, they will take some approximations taking into this sum, and then they will have some calculation for you. Okay, so actually this is what they will approach. Okay, they will approach. Okay. 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 Now I will move to a definitions that is related to this. Okay, related to what we have this area. Okay, and I will connect directly to definite integral. Okay, so I'm trying to combine, if you have the textbook, 5.1 and 5.2. Okay, because I think we are not really uh, doing more in those 5.1, 5.2, because I think that is much more about intro, because the calculus part that you need in the future is getting started from 5, I think 5.3, around 5.2, 3, and so on. Okay. This one is just about the brief intro. Okay, now let's say we have a definition here. Okay. So let me start with the definition of the uh, definite integral. Okay. So if f is a function defined for a, b, okay, the interval a, b, we divide a, b into subinterval. This is what we have done before. We divide of equal with this delta x for the width of the rectangle, b minus a divided by n, and let x0 equal a, and then we have x2, x1, x2, x3, and so on until xn. This is equal b, and let x1, x2, this is the sample point with the asterisk, be a sample point, and x1, xi, the x is lies in the subintervals between the, okay, so the sample points we take is between, so if we have the rectangle, the sample point should be in the around here or around here. Okay. Okay. Then the definite integral of f from a to b. Now we are going to introduce this integration. So the integral from a to b of our function f of x, and then we say the dx, this is equal with the limit as n approaching infinity of our sum from I equal 1 until n f x I. This is a sample point, and then the x, delta x. And this should provide, okay, this should provide the limit exists and give the same value of all possible choices of sample point. And because of that, or thus it is exists. And we say as our conclusions, if the limit exists, then the function is integrable on the interval AB. Okay. This is not same. Okay, so this means that this words here, the limit exists, okay, which means that we need to have this limit exist. Okay, of course, we should have the continuity and everything else. It should be fit with our limit, and then it gives the same value of all possible choices. So any sample points that we put into our integral here, they will end with the same results. Okay, they will end with the same results. And if that happens, then this whole thing exists. And because it exists, we can conclude that the function f here is integrable. We can integrate this f. Okay. Okay. Now from here, okay, let me take some times to look on what is uh, the actual calculations in our integral. Okay, before we learn the some integral formula. Okay, so if we have f of x, x cubed minus 6x, okay, and we have if we want to calculate area under the curve, okay, in this f, and then the interval is from 0 to 3, okay, then based on our definition, we take the limit let me show you this for a while, okay, just for the intro. So based on the interval here, the delta x is 3 minus 0 over n, or 3 over n. So our x, the sample points is 3I over n. Okay, and then we take the limit. And then we take this. Okay, and look our functions here. We have x cubed minus 6x. Okay, so let me take limit. Let me take this 3 over n outside because it's not our calculation with I, right? Okay, and we have this sigma I from 1 to n. The functions is 3I over n cubed. It's x cubed minus 6x minus 6 3I over n. Let me move to the right side here. So we have the limit as n approaches infinity. 3 over n. Let me just calculate. Cube becomes 27. I cube over n cube minus 18i over n. Okay, let's separate the I from the both of this. Okay, so I want just so I will put this 27 over n cube going outside. We'll have I cube, and this part will be also 18 over n. Let's try put outside. So 27 multiplied by 3 is 81, right? 81. 81. So this is n over n with power of 4. And this will be I, and this will be I cube. Okay. Okay, same way. 18 going to 3, so this will be here. So 18 going to be multiplied by 3 is minus 54 and squared. Okay. And this will be sigma of I. Okay. Okay. Now based on our notes, okay, we have I cube, that is n plus 1 over 2 squared. And this is I is n plus 1 over 2. Okay. Now we have limit. This will be or maybe let me write first. Let me write this first. This is n squared plus n over 2. This is n squared plus n, and this is squared over 2. Okay, and this is 81 and over and with power 4. Okay, I will move these 2 squared going outside and n4 going inside. Okay, so let me exchange this. This will be 4, and this will be n squared, right? Because it's squared, and 4 going inside. So we will have 1 plus 1 over n. The same thing here. It's going out, this 2, and then this will be n squared. So this will be 4. This will be 27. 1 plus 1 over n. Okay. Now we have limit 81 over 4, 1 plus 1 over n, let's forget squared, minus 27 1 plus 1 over n. So check the limit. So this will be 81 over 4 minus 27, or it's around negative 6.75. If we check the calculator, this will be at least the results. So your calculator will be approaching through all these computations actually. Okay, so why it's negative? So if we check the graph, okay, if we check the graph, it is maybe like okay. So this is x equal 3. This is x equal 0. Okay. This is the y or f of x is x cubed minus 6x. Okay. If you look here, we have at least how do we define our area under the curve? This is our curve, right? Where is our area that we are going to look for? Yes, in between this x and our curve. So if I take some color here, let's say we have, let's say blue. So this is the first, let's say this is the A1, okay? And the other, let's say the red color here. This one, this is A2. Okay. By looking at this area, this A2 is in the negative side, right? This is positive side. Which one is bigger? The negative one, right? That's why it's negative. Okay. So we may have the some visuals like this. Okay. Maybe like having the, or maybe the just random. Okay. So this will be the negative. Maybe we take until here from 0 to some x equal maybe c. Okay. So this will be positive. This will be positive. Okay. So this means that we have this curve here, plus, this is also plus, this is negative. Okay. Okay. And probably from this point of view, we can actually separate the integrations, right? Or separate the sum if you want. Okay. We can take 0 until some point here. You can take if we can find this x, and then from this x until 3. Okay, we can also think like that. Okay. Okay. Let's move to another uh, area of topics. Okay, at least, okay, by definitions, this is actually what is really happens. Okay? We are taking some the sum, the sigma notations, and we calculate, and we have this result. Okay? Okay. Next is we'll talk about the, let's see, about the property. Okay, the property, because I already show you the positive, negative, and in our area graph, the area under the curve. If we have integration from A to B, okay, of course this is uh, area under the curve from interval the x0 is A until the endpoint is B. Okay. Okay. This is actually based on what we have, okay, from the previous one. There is positive, negative. Okay. I can say that this is the negative of from B to A of some same function here. Okay. Okay. We can take some conclusions. And if we have compute on the exact interval, which means that there is nothing there, right? So this means that this is actually a 0. Okay, it's get nothing because subtracted by each other, right? And if we have a constant, the x of c is constant, then this will be resulting c, b minus a. Okay, and then if we have a, b, f of x, if we plus with some functions here, we can separate that. Or minus also similar property. Okay. Also, if you have the constant, again the constant, and f of x, the x, this is, we can take out the constant. Oh, it says bigger. And we have also, we can separate the interval. So if we have interval c between the a and b, c, b. So the c is in between a and b. Okay, at least this property that is very basic in our definite integral. Okay. Okay. Now another property. Okay. In our integral. Maybe let you finish first. Or maybe before that, maybe if there are any questions. Any questions? No, right? Okay. Let me check the what time is it? Oh, before this property, I should give you some notes. This is just a short note about the midpoint rule. Okay. So we have, from the beginning, we have left, right? Left and point. We have right and point for the rectangle under the curve. We have also midpoint rule, which is if we have the integrations from a to b of f of x dx, we can let them to be or approximated. Now, instead using the sample point, we can also use the midpoint rule to approximate. The delta x the same with the other, and the midpoint is half of the or we call this the midpoint of okay. For example, if you have the rectangle is maybe this is the delta x, this is 0 and maybe 2, then your midpoint will be this one. Okay. And this is your midpoint is here. Okay. This is the rectangle here. Okay. That is just a short notes. That is, we can also get the midpoint rule. Okay, and then property, and also the let's see. Okay. Okay. We have the comparison property of integral. Okay, if the functions is positive or 0, and a is less than x less than b, the interval, then integral of a to b fx dx is positive. Okay, and if the f of x is, if you compare with the g of x, is greater than g of x for the same interval, then this is greater than the g. F is greater than g. Integral f is greater than integral of g. If we set some value, okay, if we set some value, the small m and the capital M, and the function f is in between those two values at the same interval, then if we integrate, then this will be resulting in which m, the small m and the capital M is, if we can describe in the graph, let's say this is the f. Okay, this is the PM, this is the small m. Okay, or maybe if it's not clear, let me write here. This is actually integral of a b dx. Okay. Okay. Uh, okay, the next section, I think this will be the last part on our course. And I think we will continue to next week to give you more understanding on the calculus. Okay. Okay, this is the but before we start the new section, let me give you some brief idea. Okay, so we have integral. Uh, we know that its name is antiderivative, or this is indefinite integral from the perspective of derivatives, right? And we have the connections there, and we also have the uh, let's say geometric approximations, or we say that this is the definite integral. Okay, and to connect this integral to derivative, we need something here. We call the fundamental theory or theorem of calculus to connect the integral and derivatives. Okay. Okay, let's say we have again, this is A, B. Now, I will use another variable instead of x. Okay? I will use variable t. Okay? And I will write the functions as y equal f of t. Okay. Okay. Now let's observe the area only up until here. This is the area. Let me take some color. And let's say this area is g of x. Okay. The whole area, the yellow one, is the g of x. So that this is up until some x. Okay. And right here, that the area for g of x is integrations from a to some x of our f d dt. Okay. So this is the first part of our fundamental theorem of calculus. Okay. So f is continuous on the AB, and x is varies between a and b. And observe that g in the area here, it becomes dependent on x. So we can have this g of x. We change the x. It can be changing depending on x, the value of the area. Okay. So if f is continuous, then function g defined by this part, and then we say that g of x is continue on AB and differentiable on AB and g prime, maybe right here, and g prime of x is equal f of x. Okay. Maybe if you're not familiar with this g, maybe I can write with this the big F, like the antiderivative. Let me write one more time here in the second page. Let me write a second time here. Let me write with this big F here. Okay. I think it's better because on the previous chapter, you know that the antiderivative, right? And this is the same graph. This is F. Okay. This big F is antiderivative of small f. X is on between here, and the big F is continuous and differentiable on. Okay, notice that I'm using different bracket on this differentiable. I hope you understand. If you understand what that does that mean. Okay. So f of x. Oh, let me write with the black color. When we take this first derivative, we take the first derivative of both sides. This will be resulting. Let's just write this, and this will be resulting this f. Or we can write f prime x is, okay. And based on this theorem, okay, we say that every continuous f has antiderivative f. So from this moment here, we can link the derivative to integral. So if you see any continuous functions, every function that has continuous, it will have the antiderivative, which means that we can actually uh, integral that function. Okay, that's the first one. I think this is the first one. The second one is if f continue on a b, then we can also say that this can be written as this, right? Where f is, and it's actually similar writing but different structure. If is f is antiderivative of small f, and the f prime is equal to f. Okay. There is a proof. I think we still have time. Let me write the proof. Okay, based on these two uh, wordings, let's say that every continuous function has antiderivative, and we also have the net. This is actually it's called the net theorem. Okay, so suppose f is continue on a, b, and a, and this is the interval. If the antiderivative is equal okay, let's say we have x and x plus h on the same interval a, b, then f x plus h minus this fx is equal integral of a to x plus h. So we are just exchanging the x and x plus with x plus h. And this is the x. Okay. Okay. Now we have x and x plus h. Okay. Let me simplify this and making this a into x plus h becomes 2 because we have x in between it, right? Between a and x plus h, we have x, right? So I can write this as a to x, okay, and plus x to x plus h and minus a to x, okay? So this is a x plus h become a x and x plus h, okay? Now, if you see from this expressions, we can cancel this part with this, right? Okay. So we can cancel this left one here and the right one. Okay. So let me write. Still we have f, this big F here. Okay. Okay. For h is not equal 0, we can multiply both sides with 1 over h. So divide by h like that. And the right one will be having 1 over h and having this x plus h, f of t dt. Okay. And we can assume that h is going to be positive and f is continue on x to x plus h. Okay, then this is what we have. Okay. Okay, to continue this part, we need to have another theorem. So let me mark this into first equation. We will going to visit this formula again. Okay, let me write some notes. But I think I cannot finish by today. But let me write first. We call the next theorem will the extreme value theorem. So suppose there are u, v on the interval x and x plus h. And the f u is small m. The f of v is the big M, like that. We define this as our minimum value, and this will be the maximum value, like the visuals that in the comparison theorem. Okay. So if we can take this. Let's say this is our m. This is small m. This is m. The big M. This is small m. This is u, and this will be v. Okay, so we start from writing the comparison theorem that we have learned before this slide, and we say that the integrations of f of x between a and b is in between this value, minimum value and maximum value. Okay. Now, similarly, we are going to compare this expression, and let's write this expression back to here. So, and let's change b minus a with h. Okay. And let's just say that we have f of t dt and h. Okay. Let's multiply with 1 over h all these terms. That is, we have the small m, we have 1 over h, and then integral from x to x plus h. And that will be our result. And if you look the small m, that is fu, we can also write that as fu, and we can also can write these terms into these terms. Okay, it's the same same value, so we can write this. Okay. Now we can imagine, okay, as h getting closer to 0, okay, what will happen to u and what will happen to fv? And of course, we look here. If we have h is getting 0, everything will be going to closer to x. Okay, so this is going to be closer to x. V also going to be closer to x. Okay, now by limit, I think I can finish this. Yeah, by limit, as h getting closer to 0 of f of u, you can say that this limit is getting closer from u to x f of u, and we can say that the f of u is getting, or it is getting to be converted to f of x. Okay. The same way for our f of v, as h getting 0, this will v will also getting closer to x, and this will be also resulting the same f of x. Okay. Now, conclusions. because this is actual limit, right? Limit. Remember, by squeeze theorem and limit, then because this is f of x, this is f of x, right? Then the middle part also f of x. Then limit as h approaching 0, and that's why the f is equal to this. So whenever you have the a to x, some f of t dt, so if we integrate and then differentiate, we will go back to original f. Okay, I think that's it for today. Okay, until this is proof. Okay. Okay, any questions? Any questions? Okay. Okay, I hope you get this one. Okay, and it's I hope you still remember this squeeze theorem. So actually, because of this theorem, the fundamental theorem of calculus that connects the derivative and integration. So we cannot say that we learn chapter 1, 2, 3, 4, 5, 6, 7, and we learn maybe in the second part, or chapter 5, 6, 7, or 8. Um, we took that like a partial or parts from the total chapters. But actually, when you learn the chapter 5, 6, you still need something from the first part. Okay. So to understand the integrations, you need to understand the derivative. So you cannot learn chapter by chapter by chapter. You need to at least take some parts of the previous chapters going to take into the next chapters. Okay. And because we have two calculus classes this semester and next. Okay. I hope all the knowledge from this semester you still at least remember uh, the concept in the next semester. Okay, because in the next semester there will be a lot. The content will be more than this one, and if I don't have really much time to explain all, because sometimes you need to review the calculus one, and I need you to review by yourself. Okay. Okay. Any questions so far? Okay. I think today we are just going to have like an intro, and so I don't really prepare any feedback for you guys. So yeah, I will end the class today up until here. So if you have any questions, you can write on the chat box if you want for the online students. Okay. So this will be the end of our lecture. So if you would like to leave the Google Meet, that's okay. Yeah. Oh yeah.